You know that feeling when you're in an elevator and it suddenly drops? Your stomach lurches, right? Well, Einstein would say that's not gravity pulling on you. In fact, he'd say gravity isn't pulling on you at all. And once you understand why, you'll never look at falling the same way again. So here's the thing that bothered Einstein. Newton told us gravity is a force, like when you pull a rope or push a cart. Makes sense, right? The earth pulls you down, the sun pulls the earth around. Simple. But Einstein had this nagging question. How does the sun reach across 93 million miles of empty space to pull on Earth? There's nothing there. No rope, no chain, no invisible hand. Just nothing. How does the sun even know Earth is there? Newton basically said, look, I don't know how it works, but here's the math that describes what happens. And the math was brilliant. It worked, but it didn't explain the how. That's what kept Einstein up at night. Because in physics, when something doesn't make sense, it usually means we're thinking about it wrong. So Einstein did this thought experiment. Imagine you're in an elevator in deep space, far from any planets or stars. You're just floating around, right? No up, no down. You're weightless. Now imagine someone outside starts pulling that elevator upward with a constant acceleration. Suddenly, your feet hit the floor. You feel weight. If you drop your phone, it falls to the floor. Here's Einstein's question. If you couldn't look outside, could you tell the difference between that elevator being pulled upward in space or just sitting still on Earth? And the answer is no. There's no experiment you could do inside that elevator that would tell you which situation you're in. The feeling is identical. Think about it. When you're standing on Earth right now, you feel the floor pushing up against your feet. That's what you actually feel. You don't feel the Earth pulling you down. You feel the ground pushing you up. Same thing in that accelerating elevator. So Einstein said, wait a minute. If these two situations feel identical, maybe they are identical. Maybe there's no difference between being in a gravitational field and being accelerated. Now here's where it gets wild. What happens when you're in an elevator and the cable snaps? You start falling with the elevator. And during that fall, before you hit the ground, you're weightless. You float inside the elevator. If you let go of your phone, it just hovers there next to you. Why? Because you and the phone and the elevator are all falling together at the same rate. The astronauts on the International Space Station, they're falling. The station is constantly falling toward Earth, but it's also moving sideways fast enough that it keeps missing Earth. That's what an orbit is, just endless falling, and that's why they float around. They're in free fall. Einstein looked at this and had a radical thought. What if free fall isn't something happening to you? What if free fall is the natural state? What if you floating weightless is what things do naturally? And it's the ground that's doing something weird by stopping you. Think about it like this. When you drop a ball, Newton says gravity is pulling it down. Einstein says no, the ball is just moving naturally through space, and it's the ground that accelerates up to smack into it. I know, that sounds backwards. The ground isn't moving up, but stick with me. Here's what Einstein realized. Space and time aren't separate things. They're woven together into what we call space-time. It's the fabric that everything exists in. Now, mass and energy do something to this fabric. They curve it, they bend it, like when you put a bowling ball on a trampoline. The trampoline surface curves down around the ball. Imagine you're on that trampoline far from the bowling ball, and you roll a marble. It goes in a straight line, right? But as the marble gets closer to the bowling ball, it starts curving toward it. Not because the bowling ball is pulling it, but because the marble is just following the curved surface of the trampoline. That's what planets do. The sun is so massive, it curves space-time around it dramatically. Earth isn't being pulled by the sun. Earth is moving in the straightest possible line through curved space-time. That straight line just happens to be an ellipse when space-time itself is curved. You know how when you try to draw a straight line on a sphere like Earth's surface, the line curves? That's because the surface itself is curved. Same thing here, except we're talking about the fabric of space and time itself. So if objects in free fall are just moving naturally through curved space-time, why do you feel weight when you're standing still? Here's the beautiful part. Right now, you're trying to move naturally through space-time. Your natural path would be to free fall toward the center of Earth. But the ground is in the way. The ground is made of atoms, and those atoms are resisting being compressed. They're pushing up against you. That push is what you feel as weight. The ground is constantly accelerating you upward, preventing you from following your natural path through space-time. It's like if you're driving down a curved mountain road. To follow the curve, You don't have to turn the wheel if the road just curves naturally. But if there's a wall blocking the natural curve, you'll slam into it. That's what the ground is doing. It's blocking your natural motion. This is why Einstein said gravity isn't a force. Forces push and pull. They change your motion. But gravity isn't changing anything. You're just following the shape of space-time. It's the ground that's actually forcing you to accelerate upward. And here's something even wilder. If space-time is curved, then not just your path through space is affected. Your path through time is affected too. Light always travels in straight lines. But in curved space-time, those straight lines curve. This is how we've actually proven Einstein right. During a solar eclipse in 1919, scientists observed starlight bending around the sun. The sun's mass curved space-time so much that light from distant stars bent around it. And time runs slower in stronger gravitational fields. Or more accurately, time runs slower deeper in the curve of space-time. An atomic clock on the ground runs slower than one on a satellite. We have to adjust GPS satellites for this effect, or your phone's map would be wrong by miles every day. This isn't science fiction. This is measured reality. And it all comes from Einstein realizing that gravity isn't a force pulling things together. It's the shape of the universe itself. So next time you drop something, remember this. That object isn't being pulled down. It's moving in the straightest possible line through a curved universe. And you're not sitting still. The Earth is accelerating you upward right now, pushing you away from your natural path through space-time. Newton gave us a brilliant approximation that works for almost everything we do. But Einstein gave us the deeper truth. He showed us that gravity isn't a force at all. It's geometry. It's the shape of reality. And honestly, that's so much more beautiful than just things pull on each other. We're not being pulled through the universe. We're surfing the curves of space-time itself. Pretty cool, right?